It is possible to do statistical analysis from within ArcGis, but I always find it more interesting, and also there are better tools of statistical analysis outside ArcGis. In this case, I'm opening up the data material in one of the more common, perhaps not the most advanced statistical machine, but nevertheless it's SPSS and it works well enough for these kinds of things. So what I need to do is actually to press the open, and I'm in the folder where I've got the cafe material, but I can't see anything, and that's of course because the predefined file is the SPSS file. But if we choose the dbase, we will find all the things that we know were there from the beginning, all the files that are part of the material that is being saved from ArcGis. And in order to find out which one is what's being saved the latest, we can always of course use the changed latest kind of command and find that this one, let me see, this one here was the latest of them all, so cafe plus raster dbase, which means that we've got all the material, including the ones where we sort of fed the material with the raster information from the underlying one, is the one we want to use. So I click open, and we have to see, oh, there it is. It became a very small file for a little while there, and it still does. We'll see what we can do in terms of how to make it work. Let's see if we can adjust it according to the page size that we've got. You'll have to wait for me, guys. So there we are. So in this case, we've got a few different things. We've got two string variables on names and IDs of the cafes. We got the code, which is the OpenStreetMap code of cafes, and the name, in fact, stating cafe. We got the name of the cafe, and we got the variables we constructed: the distance to the station, the value that we generated from the raster, and the x and y coordinates. In fact, the only variables we would need are the x and y and the ones we want to use in regression. All the other ones, these ones, could be deleted, because in the next step we want only the coordinates and the statistical material to be part of our map. So to really show that we can throw them away, I'm going to do the right click and just do clear, and that will be it. So, and I'll also move the x and y variable up here so we can see more clearly where we are located. So the x and y, the distance to the park, the distance to the station, in two different formats, constructed so on purpose, of course, and the raster value. And the raster value is the value that represented what's the share of cafes per square kilometers. And in this case, we could in fact change it here. So I can double click here and say cafe per kilometer, and that will be an easy way of solving sort of the computation of that. In the subsequent step then is to find out how we can do any kind of regression. The hypothesis I would share with you is that the share of cafes per land is positively correlated with the distance we've got to the stations and the parks. So if I assume that I can use in a regression, if we go for analyze regression, linear, the cafe per square kilometer as a dependent variable, which means this is the question, this is the y variable, this is what is being measured. The other one here being distance to park and distance to station being the independent variables we add there. And in those cases they are contributing to saying every little change in a distance to a park or a distance to a station, in what sense is that likely to change the frequency of cafes, or is there any correlation? Of course, whatever we find, we cannot say that there's a causal relationship. We can only point to correlation between the two. We can point to the fact that the increased or decreasing distance to parks are correlated to cafe per square kilometers. That's what we can say. We satisfy ourselves by that and just press an OK, and in the next phase we will see automatically the results are turning up. And if we look at this one, we can see that we've got an explanatory power of 1.28 if we take the adjusted R-square, which literally means that 12.8% of the cafes per square kilometers is being explained by the distance to parks and different stations. That is not to say that we haven't sort of included a lot of sort of proxies and variables or endogenous things that might point to other things and be part of other objects. We're just stating that 12.8% of the variation is being catered for. If it's the truth, that's another matter. If we look at the results, we can see there's a negative correlation, which means that for an increasing amount of if there is an increasing amount of cafes per square kilometer, it is going to be a decreased distance to parks, which makes sense. If there's shorter distance to park, it means probably that we are in a dense urban area, and that increases the number of cafes, and the same goes for the stations. We can by the t-test see that the distance to the station is stronger because it's 8.1 compared to the 4.6 when it comes to the distance of the park. So the station value seems to be a little bit stronger. If we look for the absolute value, we see that this is sort of it's weaker, but the effect is stronger. It's all highly significant, so there's no doubt that there is a correlation. It's not a random thing we see. If we go back to this, one way of looking at the material is to save the predicted values and also the residuals and see how they look on a map. So we can both take individual data from the map, bring it to a statistics software, but then bring it back again. So what we're going to do is to do analyze, regression, linear, and we're going to click on save. And here we've got two things I want to check: the predicted values and the residuals. The predicted values is simply doing what we think given the information we feed the regression. The question being, what's the number of cafes per square kilometer, using the only information it's got, the distance to park and the distance to station. What is the predicted value of cafes per square kilometer? In other words, we've got this answer, but we want the predicted value. And the residuals communicate the difference between the estimates and the observed. So we get the error, what we fail in communicating. So these two are interesting to have. If we now press continue and redo regression, we end up with the same set of material again. We've got the same, there you go, the same adjusted R-square value. We get the same coefficients. We've got everything's identical. But what we got this time is two new variables. One called predicted value, or pre1, the other one being residuals 1. So we can see how much it is. So, in other words, we had 1.19 cafes in this location. It predicted 13, which is a pretty big residual. But in other locations, it goes in other directions. It falls under all kinds of categories, right? So this is what it looks like. What we want us to do now is to save the material in a format so that it could be reopened in ArcGis, and we can watch the statistics and see how it fits to the geography. That would be interesting. And what we do in order to do that is actually to save it into a format that it can use. So I'm going to save it, save as, and I've got a few to choose between. But I'm going to use the one that I find when it's not too many cases, as in this case it's not too many cases. I can use an Excel. Excel is good at handling things like decimals, and it doesn't distort names if you've got string variables. If you're using D-base format, you could probably store more information, but it usually sort of becomes problematic when you've got string variables and some other kinds of things. So I'm going to write regression results, and I'm going to save it. And it's already done. So in the next step,